Hello everyone, this video is going to talk about L'Hopital's rule. Here's the outline. The first part is proofs of L'Hopital's rule. We will provide 6 versions of L'Hopital's rule so that you will learn more than reading the textbook Calculus 9 edition by Stewart. The second part is applying L'Hopital's rule. The tabular here shows the work assignment of our team as well as the members of our team. The first person is Jiang Yikai. He is responsible for the exercises to tell you how to apply L'Hopital's rule as well as choosing the template for this PowerPoint. The second person is Xu Yiyou. He is responsible for the proof of L'Hopital's rule as well as this outline. Before start with our proofs, I'm going to show you a new function, a new limit function. The input of this function is function f and a real number a. If the limit exists, it will return the limit, which is a real number. If the limit doesn't exist, it may return positive infinity, negative infinity, both-sided infinity, or nothing. The abbreviation NOT will be used frequently in the subsequent proofs. The both-sided infinity definition is shown on the right, and here is the absolute value of f greater than n. The Cauchy's mean value theorem, which is abbreviated as the CMVT, will also be frequently used in the following report. Here is the first form of L'Hopital's rule. The condition is from here for all a to the limit equals 0. Under the conditions, it's the limit of f prime over g prime is a real number or infinity, implies that the equivalence of the two limits. In order to prove it, I mark the techniques on the textbook. I define the two functions, capital uppercase F and uppercase G. The definition at a, which equals 0, is added to the original function f. F and g are both continuous on this interval. The CMVT allows this result. I assume that the limit of f prime over g prime is a real number L. Then this is due to the assumption. And for any difference epsilon, I can find a delta such that for all x in this open interval satisfies the following property. Then I get that the limit of f over g is also the real numbers L, and the equivalence of the two limits under the assumption is proved. Under the other conditions, the equivalence can be proved likewise. Here is the second form of L'Hopital's rule. The difference is that the condition requires function f and g be continuously differentiable. Then it allows a more beautiful result, that the two limits is equivalent to each other. If the right hand side is nothing, then the left-hand side is nothing. If the left-hand side is both-sided infinity, the right-hand side is also a both-sided infinity. I only have to add a proof to show that the limit of f prime over g prime is nothing implies that the limit of f over g is not also. I achieved it by showing that this known statement, that is the limit is a real number or infinity implies that the equivalence. I assume that the limit of f over g is a real number L. This is obtained from the CMVT, and this is the assumption. This is the continuity of f prime over g prime. Combine them together, I get the desired result, that the f prime over g prime, the limits of f prime over g prime is L. Here is the third form of L'Hopital's rule. The difference is that the limit of f and g are infinities. The result is that the limit of f prime over g prime is a real number, implies that the equivalence of the two limits. I assume that the limit of f prime over g prime is a real number L. Then here I set the epsilon to be epsilon over 3. This is due to the assumption. Then I apply the CMVT. The diagram above is used to demonstrate the relevant positions of the variables mentioned in this expression. Here I divide the enumerator and denominator simultaneously with g of y, and here I multiplied the left hand side and the right hand side by this term simultaneously. Then I obtain this result. This term won't be 0 because the g prime of y is not 0 over a from a to b, and if the open interval a and m is small enough, then the g of y is always non-zero. So it allows this inference. Then the trigonometric inequality gives me this result. I also set another delta 2. That this is due to the limit of g of y is infinity as y approaches a from the right. Then I choose the delta to be the minimum of the 2 delta. I get this result, QED. All of the three forms can be extended to s approaches positive infinity. To achieve that, I prove the following theorem first. I call it the reciprocal law. The condition is only the condition only requires that f is a function. I define the condition into these 5 situations. The left-hand side is a real number, positive infinity, negative infinity, both-sided infinity, and the left-hand side is not. Under the 4 conditions, the equivalence can be proved by applying substitution law. For the remaining one, I use this logical relation. I prove this, then I prove this to be true, then this is also true. Here is the proof of the situation that the right hand side is a real number. The other one can also be proved likewise. So here, I get the extended first form of L'Hopital's rule. The proof is shown in the next page. Here I also put the first form of L'Hopital's rule so that you can compare the difference between them. Here I use the reciprocal law and check the condition of the first form of L'Hopital's rule, then combine them together and get the result. At least the limit is equivalent to this limit. Another two extensions are left to your exercise. I left to you as an exercises. Also, I have the other four exercises for you. These three exercises is to extend the theorem to approaching A from the both sides. And the last one, a modified third form of L'Hopital's rule, is that the condition of the result isn't a real number but infinity. Thank you for listening. My report has come to an end.
So, how to solve our first example? We need to check if we can use the rule first. The limit as x approaches 0 to e to the power of x minus 1 equals 1 minus 1, which equals 0. The limit as x approaches 0 of x squared plus x equals 0 plus 0, which is equal to 0. Also, we need to check if 2 plus 1 doesn't equal to 0 when x approaching to 0. So we can see in this picture, by an easy calculation, the limit as x approaches 0 of 2 plus 1 equals 1, which is not equal to 0. So, now we may do a further calculation. The limit as x goes to 0 of e to the power of x minus 1 divided by x squared plus x equals the limit as x goes to 0 of e to the power of x divided by 2 plus 1, and finally equals to 1. So the answer is 1. So here comes our second example. We will now validate the conditions for L'Hopital's rule. The limit as x approaches 0 from the right of x equals 0, but the limit as x approaches 0 from the right of 1 over x equals infinity. So we will use this form of the equation later. The limit as x approaches 0 from the right of the natural logarithm of x equals negative infinity. Since we have done the check, we may now move to the calculation part. The limit as x approaches 0 from the right of x times the natural log x can be rewritten as the limit of natural log x over 1 over x. Applying L'Hopital's rule, this becomes the limit of 1 over x divided by negative 1 over x squared, which simplifies to the limit of negative x, and this limit equals 0. So, the answer is 0. This concludes our presentation. Thank you all for your time and attention.